Good evening, good evening, good evening. We are live. Indeed, we're live. I'm here. I am here. My hair is a little weird, but I am here. How are you doing? We are live. I hope to see many of you live. I hope to see many of your comments later on as a video upload. If you're seeing this as a video upload, I hope you'll let me know soon whether you can see me and hear me okay. And we're live. We're live. We're going to be talking about the expanding universe, probably referencing Stephen Hawking's book. So we're live. We're here. In fact, Suji Mama is very much with me right here. Steven Spears! Hello! Steven, how are you? How are you doing, Steven? I took a shower and here I am. Here I am. Here I am. In the flesh. Quite fresh. From a shower. From the bathroom. Steven, how are you doing? How's everything going? How's Virginia? And let me share the live as I speak. Indeed, as I speak. And thank you for joining, Steven, so quickly. And, in fact, just got the notification. Thank you. Thank you so much, Steven. Steven says I'm good. And you? Just got the notification. Hello. Thank you for liking the live. Thank you, Mike D. Could you please like and love the love the live. Like, share, subscribe. Thank you. Hello, Steven. Hello, Mike D. Mike D says, I love you. Like, share, subscribe. Thank you so much. Thank you. I see the 2 people and the 2 likes, and I'm thrilled. Indeed, I'm thrilled. Indeed, here is Stephen Hawking's A Brief History of Time. We started to talk a little bit about what even time means, what time even means, and how it might not be conceptually meaningful to talk about time unless we talk about the beginning of the universe. In fact, with the Big Bang is when maybe the definition of time really starts, is something we were talking about from this book. And also the book talks about the contributions of Newton and even way back Aristotle, Ptolemy, all of the shenanigans and the happenings of the solar system model and everything like that. That we have gone through in the history of science. So skipping through that, we're going to actually talk about the expansion of the universe today as noted and worked on by Stephen Hawking, as shared by Stephen Hawking with his book. So hopefully that's going to be a lot of fun. Hi, Harper. Hello, Harper. Hello, Dominic. Hello, Stephen. So yes, I have looked up that this book talks about the expanding universe in chapter 3 of the book, and so we will be referencing that today, and we will not spend too much more time on chapters 1 and 2 because we've kind of covered that already when we talked about the 20th century physics and when we talked about Einstein's work and a little bit touched upon Newtonian mechanics and things like that. Thank you for liking. Harper, did you like the live? Dominic, did you like the live? Everybody else, did you like the live? Thank you so much for being here. Can we get 10 likes? That would be amazing. Sorry, my hair is a little crazy today. Didn't quite do my normal routine, but here I am. Rubel Ruma says good. Hi. Hi, Rubel. Everybody's saying, everybody who wants to say hi, do it now. Do it right now. I demand. Newton was a crazy guy, says SG. Newton was very passionate. He worked very solo most of the time. And he had a doggy called Diamond. I approve. I also like animals. And I like the company of animals. Nate Hartman says hi. Hello, SG. Hello, Harper. Hello, Rubel. Hello, Nate. Hello, Harper. Again, hello, Harper. The mod is very hard at work. Thank you so much for modding. Steven says Olay. Rubel says country name. The country name of this country that I'm in currently is the United States of America. I'm originally from India. If you would like to share your country name, go for it. Most welcome to. Welcome to the live. My doggy's name is Rocket. Oh my gosh. Rocket. How very kinematic. He got a little mercury poisoning from his alchemy hobbies. SG says, Newton, that could be. I don't know that story, but thank you for sharing. Steven Spears says, I have 3 cats, Mr. Kitty, Ocean, Luna. Yes! That's right. Steven here is a cat dad. And we have a very similar number of kitty cats between the two of us. So thank you so much, everybody, for sharing. If you want to say hi, feel free. No holding back. Go for it. Go say hi in the chat. I will read your comment. I will read your chat message. I will read your username. Give you a shout out. Thank you. Morer says, I'm not a cat. Hello. That's okay. Are you a doggy? Because doggies are welcome too. In fact, people are welcome too sometimes. Tarzim K said something and then retracted it. So I know not what you have said because I can't read that quick. Jerry Sullivan says, I like your hair. Thank you. If I get sponsored by a shampoo, I will let you know. So far, that has never happened. Morer says, no, I'm hamburger. I once mugged a guy walking his cat. Oh my goodness. Tarzan K, I don't know that we like that at all. Steven says, Luna loves to play chess. We have a wooden chess set. Ooh. And Luna loves to knock the pieces off the board. It's so cute. Yes, that's true. My children are much like that as well. Okay, we will get going here. So what I'll do is I'll do a little bit of a book reading from Stephen Hawking's Brief History of Time and give you a little introduction on the expanding universe as written by him. We have, of course, talked about cosmology, remember, in our previous lives, especially the lives that are either have cosmology in the name of it or universe or something. Sometimes the live streams are not quite named appropriately, so apologies for that. But hopefully you will come across our cosmology lives where we have talked about this topic quite extensively. Jerry Sullivan says, what time is it in the country? It is 10:57 p.m. Thank you for asking. I am somebody who kind of struggles with time, and by asking, you've let me know what the time is myself. Eat the pages to absorb the knowledge. I watched her knock off 4 or 5 pieces of the homemade chessboard. My brother made the board. I once mugged a guy that was walking a cat. Nathan, hello. Hello, and I have a beagle. Beagles have a lot of energy. Good hunter dogs. How is your beagle, Nathan? I will say hi again, everybody, once I take a break from the reading. I'll keep going for now. Thank you so much for being here. Welcome to the live. Welcome, welcome indeed. Thank you so much. If one looks at the sky on a clear, moonless night, the brightest objects one sees are likely to be the planets Venus, Mars, Jupiter, and Saturn. So now, of course, as we know, the brightest object in the sky after the sun and the moon, of course, are Venus, Mars, Jupiter, and Saturn. Nobody's saying that any of these are brighter than the sun or the moon. I ate that bagel. I think you mean bagel. This is a very animal-loving channel, so I think we want you to mean bagel, not beagle. I have a calico tabby named Luna. She's the big one. And a lynx point Siamese cat named Oliver, but we call him Ollie. Okay, so Venus, Mars, Jupiter, Saturn, there will also be a very large number of stars which are just like our own sun, but much farther from us. Some of these fixed stars do in fact appear to change very slightly their positions relative to each other as the Earth orbits around the sun. They're not really fixed at all. This is because they're comparatively near to us. As the Earth goes round the sun, we see them from different positions against the background of more distant stars. This is fortunate because it enables us to measure directly the distance of these stars from us. The nearer they are, the more they appear to move. So the nearer they are, the more they appear to move. The nearest star, called Proxima Centauri, take a little clip of that. The nearest star, called Proxima Centauri, Proxima, so proximity sort of thing. Proxima Centauri, nearest star, is found to be about 4 light years away. The light from it takes about 4 years to reach Earth. So again, 4 light years away. So the light from Proxima Centauri takes around 4 years to reach us on Earth, or about 23 million miles. So because in miles this is going to be so long, it's a little bit difficult to say these numbers in miles, but if you like to hear the same word twice, then this is 23 million miles. Most of the other stars that are visible to the naked eye lie within a few hundred light years of us. Our sun, for comparison, is a mere 8 light minutes away. So it only takes light from the sun to reach us. It takes 8 minutes. So we call it... Oh, hi. Hello, Varun. Hello, Morer. Hello, Varun. So, as you know, the light from from our own sun to us takes only 8 minutes. So that is 8 light minutes away. Our sun. The visible stars appear spread all over the night sky, but are particularly concentrated in one band, which we call the Milky Way. As you know, I'm quite obsessed with this band. I'm willing to travel to very remote locations sometimes to see this band, and in fact I hope to do that more and more going forward. But if you go to a relatively really dark place, then hopefully you can actually see our Milky Way as a band across the sky. As long ago as 1750, some astronomers were suggesting that the appearance of the Milky Way could be explained if most of the visible stars lie in a single dish-like configuration, one example of what we now call a spiral galaxy. Only a few decades later, the astronomer Sir William Herschel confirmed this idea by painstakingly cataloging the positions and distances of vast numbers of stars. Even so, the idea gained complete acceptance only early this century. Our modern picture of the universe dates back to only 1924, when the American astronomer Edwin Hubble. So we've also talked about Edwin Hubble from various books, especially from our astrophysics book, which, by the way, the textbook for astrophysics that we've been using a lot on this channel. I've been meaning to put the name and authors of it on my channel main page, like the channel description, because we've used it so much. But as far as I can remember, it is called The Foundations of Astrophysics, and the authors are Barbara Ryden and Bradley M. Peterson. And from there too, we extensively talked about Edwin Hubble's discoveries of the many galaxies that we did not know about earlier. And Hubble was the one who also classified galaxies. If you'll remember, we used his way of classifying galaxies based on morphology or shape, and we said the classifications were spiral, elliptical, and irregular. So this is the guy that now Stephen Hawking is also mentioning in his book. So really, truly, our modern picture of astronomy and how we do observational astronomy and what we do and how we think, it really is, really does come down to what we got from Hubble about 100 years ago. And so we must be very thankful to him indeed. So this is Edwin Hubble, who demonstrated that ours was not the only galaxy. So we didn't really know that our galaxy was not the only galaxy, and in fact there were many other galaxies. There were in fact many others with vast tracts of empty space between them. In order to prove this, he needed to determine the distances to these other galaxies, which are so far away that unlike nearby stars, they really do appear fixed. So I see people in the chat talking about kitty cats and pets. We will definitely spend time saying hi to... oh, Baji's not there right now, but we will definitely... I see Suji out of the corner of my eye, so we will definitely say hi to the kitty cats as well in just a bit. Hubble was forced... in order to prove this, he needed to determine the distances to these other galaxies, which are so far away that, unlike nearby stars, they really do appear fixed. Hubble was forced, therefore, to use indirect methods to measure the distances. Now, the apparent brightness of a star depends on two factors: how much light it radiates, its luminosity, and how far it is from us. For nearby stars, we can measure their apparent brightness and their distance, and so we can work out their luminosity. Conversely, if we knew the luminosity of stars and other galaxies, we could work out their distance by measuring their apparent brightness. Hubble noted that certain types of stars always have the same luminosity when they are near enough for us to measure. Therefore, he argued, if we found such stars in another galaxy, we could assume that they had the same luminosity, and so calculate the distance to that galaxy. So this is one way of calculating distance, which, remember, in astronomy is quite difficult. Understanding exactly the accurate distance to various objects is not a trivial matter in astronomy. As we just mentioned a few distances, few example distances, you will have an appreciation for that. If we could do this for a number of stars in the same galaxy and our calculations always gave the same distance, we could be fairly confident of our estimate. In this way, Edwin Hubble worked out the distances to 9 different galaxies. We now know that our galaxy is only one of some 100,000 million that can be seen using modern telescopes. Each galaxy itself containing some 100,000 million stars. So we have the picture of a spiral galaxy here in the book that I can show you in a minute. We think ours must look like something like this spiral galaxy. We live in a galaxy that is about 100,000 light years across. So our galaxy in light years across is around 100,000 light years across. So we have various numbers for distances in our own galaxy, but one of the ones that people seem to appreciate is this one, which is that it's just 100,000 light years across. So light takes around 100,000 years to go from one end to the other for our own galaxy. So it's our own galaxy is quite substantial. In other words, it's not a tiny galaxy. It's pretty big. And we've also talked about the stars and luminosities and the supermassive black hole at the center. It is not a small, insignificant kind of galaxy. It is also not considered to be an active galaxy because, as you know, as we spoke about in the past, active galaxy is the type of galaxy where most of the luminosity of the galaxy comes from its active galactic nuclei, or really active galactic nucleus for the singular for one galaxy. And the luminosity coming from such an active nucleus at the center of the galaxy basically rivals that of all the other objects put together, such as quasars was one example of an active galactic nucleus. And our galaxy is not such a galaxy. Even though we too have a very bright galactic center, we also have a substantial amount and number of stars. Yes, our own supermassive black hole is a large one as well. And we've talked about Sagittarius as well on the... Yes, Sagittarius A star is the name of the supermassive black hole at the center of our own galaxy. And we have spoke about that on the channel, and we can revisit as well if you'd like. We can talk about our own galaxy more, for sure. So Sagittarius A is the name of the galactic center. It's very bright because it's a radio source. It has X-rays, things like that. And then the supermassive black hole specifically is called Sagittarius A star. And we have some ways of knowing exactly how big that is and things like that. So we can talk about our own galactic center as well. But pretty much this is all to say that our galaxy is not an insignificant galaxy. It is quite a substantial spiral, substantial with stars and all kinds of objects type of galaxy. Very diverse galaxy. Accretion disk. Yes, accretion. A-C-C-R-E. Yes. Yeah, accretion. You got it. Accreting. As Varun Malik is saying, the accretion of mass into the black hole, by the black hole, accreting mass. So all the mass that's falling into the black hole, the acceleration of that causes all the bright radiation. So we live in a galaxy that is about 100,000 light years across and is slowly rotating. Yes. The stars in its spiral arms orbit around its center about once every several 100 million years. Our sun is just an ordinary average-sized yellow star near the inner edge of one of the spiral arms. We actually pointed out which spiral arm we're part of for our own galaxy, and we have pointed out all the names of all the different arms in our galaxy as well in a previous live. So be sure to check that out if you're interested in these types of content, the galaxy stuff, especially our own galaxy Milky Way, we've covered in quite a bit of detail. Stars are so far away that they appear to us to be just pinpoints of light. We cannot see their size or shape. So how can we tell different types of stars apart? For the vast majority of stars, there is only one characteristic feature that we can observe, the color of their light. Newton discovered that if light from the sun passes through a triangular-shaped piece of glass called a prism, so remember how Newton not only worked on mechanics, but he also actually worked substantially on optics. So this is from one of his optics work. So he actually found that if you pass light from the sun through something called a prism, it breaks up into its component colors, the various wavelengths of light you would be able to see. Thank you for liking the live. Can we get 10 likes, please? Thank you so much. By focusing a telescope on an individual star or galaxy, one can similarly observe the spectrum of the light from that star or galaxy. So just like you can break up sunlight into its individual components if you pass it through a prism, same sort of thing you can do with the light coming from a star or a galaxy that is distant from us. So not just the sun, but a different type of object. But you do that with a telescope, inside of a telescope. Different stars have different spectra, but the relative brightness of the different colors is always exactly what one would expect to find in the light emitted by an object that is glowing red hot. In fact, the light emitted by any opaque object that is glowing red hot has a characteristic spectrum that depends only on its temperature, a thermal spectrum. This means that we can tell a star's temperature from the spectrum of its light. So that's another part of this puzzle, by the way, which is that the different colors also tell us something about the object. So we can learn a lot, actually, from these types of observations. Oh, hello. Hi, John Foster. Hi, Steven Spears. Hi, Combat Sports. Missed so many lives. Oh, gosh. John Foster. Hello. Thank you so much for being in the live. Welcome. Welcome, welcome. Thank you so much for being here. Really appreciate you. In fact, the light emitted by any opaque object that is glowing red hot has a characteristic spectrum that depends only on its temperature. So, something to keep in mind. So, a thermal spectrum. This means that we can tell a star's temperature from the spectrum of its light. Moreover, we find that certain very specific colors are missing from stars' spectra, and these missing colors may vary from star to star. Since we know that each chemical element absorbs a characteristic set of very specific colors, by matching these to those that are missing from a star's spectrum, we can determine exactly which elements are present in the star's atmosphere. Thank you. In the 1920s, when astronomers began to look at the spectra of stars in other galaxies, so, we didn't really do much with other galaxies until Hubble told us that there were a lot of other galaxies with his observations. And after that, we can start to see stars. And not only that, we can start to see the spectra of stars by doing this light breaking up into its component thing. So they found something very peculiar when they started to look at the spectra of stars in other galaxies. There were the same characteristic sets of missing colors as for stars in our own galaxy, but they were all shifted by the same relative amount toward the red end of the spectrum. Yes, that's part of it too. We can estimate the composition. Exactly. So again, we will read this part again. In the 1920s, when astronomers began to look at the spectrum of stars in other galaxies, they found something most peculiar. They were the same characteristic sets of missing colors as for stars in our own galaxy, but they were all shifted by the same relative amount toward the red end of the spectrum. So because the spectrum has various colors, as you know, and these stars, they were all red shifted. To understand the implications of this, we must first understand the Doppler effect. As we have seen, visible light consists of fluctuations or waves in the electromagnetic field. So we have Einstein to thank, of course, to Einstein and others, not just Einstein, but Maxwell, Faraday. All of these people talked about electromagnetism. And then Einstein gave us the more updated theory for light and how really electromagnetic waves are connected to light. Light is made up of electromagnetic waves, electric and magnetic waves oscillating together and traveling through space is what light is. So now that that gives us the wave nature of light. We also know that, of course, light has wave-particle duality. It can also have a particle nature, and we call that photons. And again, Einstein worked on photoelectric effect as well. So if you kind of followed along when we talked about the 20th century physics, especially in the year 1905, where Einstein did like 4 different massive contributions to physics, including the photoelectric effect, as well as special theory of relativity, then you would have heard about this already, but I kind of summarized that real quick for you there. So as we have seen, visible light consists of fluctuations or waves in the electromagnetic field. The wavelength or distance from one wave crest to the next of light is extremely small, ranging from 4 to 7/10 millionths of a meter. The different wavelengths of light are what the human eye sees as different colors. So these different colors are simply different wavelengths of light, and white light is generally a mix of many different wavelengths. So the different wavelengths of light are what the human eye sees as different colors, with the longest wavelengths appearing at the red end of the spectrum and the shortest wavelengths at the blue end. So if you are red shifted, that means the wavelengths are getting longer, and if you're blue shifted, that means the wavelengths are getting shorter. So that's what's going on. Now imagine a source of light at a constant distance from us, such as a star, emitting waves of light at a constant wavelength. Obviously, the wavelength of the waves we receive will be the same as the wavelength at which they're emitted. The gravitational field of the galaxy will not be large enough to have a significant effect. Suppose now that the source starts moving towards us. When the source emits the next wave crest, it will be nearer to us. So literally, it is emitting these waves with finite wavelength. So literally, the wavelength meaning the crests and the troughs. Wave as in something goes like this, quite literally it has crests and troughs. So yes, exactly. So suppose now that the source starts moving towards us. In that case, when the source emits the next wave crest, it will be nearer to us. So the distance between wave crests will be smaller than when the star was stationary. If the distance between wave crests is smaller, that means the wavelength is getting shorter, right? This means that the wavelength of the waves we receive is shorter than when the star was stationary. Correspondingly, if the source is moving away from us, the wavelength of the waves we receive will be longer. So as simple as that, if the wave crests, distance between them, distance between the wave crests, if they get shorter, that means wavelength is getting shorter. If the distance between the wave crests get longer, that means the wavelengths are getting longer. And longer means red shifted and shorter means blue shifted. Hello, Doro. Yes, now Andromeda is a close neighbor of ours. So we will be, as Stephen pointed out, we will be colliding with Andromeda. We will finish merging with Andromeda, actually, in a few billion years. I believe it was 6 billion years. So when our sun is a giant, we will actually be a merged galaxy with Andromeda. So that's another story that we have talked about as well. Thank you, Dora, for joining. We are live. Welcome, welcome. Thank you so much. And can we get 20 likes, as Dora has pointed out? Correspondingly, if the source is moving away from us, the wavelength of the waves we receive will be longer. In the case of light, therefore, this means that stars moving away from us will have their spectra shifted toward the red end of the spectrum, or red shifted, and those moving toward us will have their spectra blue shifted. This relationship between wavelength and speed, which is called the Doppler effect, wavelength and speed, relationship between wavelength and speed, which is called the Doppler effect, is an everyday experience. Listen to a car passing on the road. As the car is approaching, its engine sounds at a higher pitch, corresponding to a shorter wavelength and higher frequency of sound waves. And when it passes and goes away, it sounds at a lower pitch. The behavior of light or radio waves is similar. Indeed, the police make use of the Doppler effect to measure the speed of cars by measuring the wavelength of pulses of radio waves reflected off of them. Thank you so much. Thank you for joining. Welcome, and thank you so much for your comments and chat messages. So as you can see, the Doppler effect is even used by cops. So it's very common. It's nothing too special. It's kind of making use of this speed and wavelength relationship. So even police people are using it. Yes, exactly. In the years following his proof of the existence of other galaxies. So now, remember, everything is coming together. If Hubble had not found these other galaxies to begin with, then we wouldn't have the star data and in fact, we used actually supernova data as well to figure out the expansion of the universe. We wouldn't have known about these other stars in other galaxies to begin with. So we really must thank Edwin Hubble for his work with observational astronomy, giving us all these other extra galaxies, if you will, to begin with. In fact, he gave us so many more galaxies than we knew about. We even used his work to classify galaxies. So after he gave us all these galaxies, then we can do the work of figuring out all this stuff that we are talking about. So in the years following his proof of the existence of other galaxies, Hubble spent his time cataloging their distances and observing their spectra. So it's kind of like he gave us all these more galaxies, other galaxies beyond our own galaxy, and also gave us a way not only to classify them, as you know, based on shape of the galaxies, based on morphology, as we say, but also these types of works, like how far away they were, his estimates for the distances they were at, and also observing their spectra. Because if you're already observing a galaxy, why not do that thing where you try to figure out, well, if I pass the light from this object, which in this case is a galaxy, what does it break up into, and things like that. At that time, most people expected the galaxies to be moving around quite randomly. So this type of observation that we're talking about now, this type of finding about the other galaxies is really unexpected. We didn't know that we would find this thing that we just spoke about the redshiftedness, the redshiftedness. At that time, most people actually thought maybe it'll just be random, maybe the galaxies will be moving around quite randomly. And so expected to find as many blue shifted spectra as red shifted ones. They thought, okay, some will be red shifted, some will be blue shifted, because it's all going to be random. Because again, remember how Einstein in his general relativity had introduced a cosmological constant to account for anti-gravity, to kind of keep everything stable. He basically figured, well, something has to be keeping gravity at bay, otherwise everything would be collapsing on itself. So if things are not collapsing on itself, I'll introduce a term called the cosmological constant, which will kind of just stabilize things. But little did we expect that the universe would not only be stable against gravity, but it would be expanding, which is what we're currently talking about. So it was quite a surprise, therefore, to find that most galaxies appeared redshifted. So they were redshifted. Nearly all were moving away from us. So when we not only find these galaxies for the first time, and then we go on to do the work of figuring out their spectra, and we see that they're actually redshifted. So they're moving away from us, nearly all. More surprisingly still was the finding that Hubble published in 1929, even the size of a galaxy's redshift is not random. How much it's redshifted is also something to be noted. It is not random, but is directly proportional to the galaxy's distance from us. So it's not just a random, oh, everything is redshifted, most things are redshifted, and it's random. No, how much it's redshifted is proportional to the galaxy's distance from us, which is pretty crucial and pretty interesting. And again, of course, we have to thank Hubble for figuring out these distances. That the figuring out the distances itself is not trivial. Sometimes the distances he estimated had to be kind of updated, especially for some special kinds of galaxies like active galaxies. But overall, it's a lot of work to even figure out the distances, okay? So, in other words, the farther a galaxy is, the faster it is moving away. The farther a galaxy is, the more redshifted its spectra was, we found, and the faster it was moving away from us. And that meant that the universe could not be static. Because remember, again, the whole point of that cosmological constant that Einstein introduced into his mathematics was to kind of keep everything stable, static, whatever. So this whole finding about the galaxies moving away from us means that things are not static. They're not static. And that meant that the universe could not be static as everyone previously had thought, but it is in fact expanding. The distance between the different galaxies is growing all the time. As in it's getting more and more. The discovery that the universe is expanding was one of the great intellectual revolutions of the 20th century. So in the 20th century, we have spoken about a lot. We mentioned special theory of relativity, photoelectric effect, Brownian motion. What else? Quantum mechanics, of course, in a big way developed in the 20th century as well. Lots of parallel things happening in the quantum world. But this fact about the expansion of the universe is really what gave birth to modern cosmology. Cosmology is, of course, the study of the universe at a large scale. So when we talk about astronomy, astrophysics, that is, it could be more specific. It could be more specific of an object that we're talking about. It could be a specific galaxy or other galaxies or stars or whatever. You could be interested in a specific object in the sky or a specific event in the sky. But when we talk about cosmology, we really are trying to understand the universe as a whole, understanding the universe at a large scale. So something like dark energy, expansion of the universe, large scale structure, the Big Bang, that is more of a cosmology topic, just to kind of clarify what I mean by cosmology. So this meant that the universe could not be static, all these galaxies moving away, as everyone previously had thought, but it is in fact expanding. The distance between the different galaxies is growing all the time. Especially the other day, I saw recently where they're finding early galaxies some 16 billion light years away now. Especially the other day. What do you mean by that comment, John Foster? I'm not totally following. Thank you so much for being here, though, everybody. Steven, Spears, Varun, John, Doro. Hello. Thank you. So. Universe cannot be static as everyone previously had thought, but it is in fact expanding. The distance between the different galaxies is growing all the time. The discovery that the universe is expanding was one of the great intellectual revolutions of the 20th century. With hindsight, it is easy to wonder why no one had thought of it before. Thank you for liking the live. Thank you so much. Yes, so the universe is expanding at a large scale. At cosmological scales, the universe is expanding, but at more neighborly scales, like Andromeda is just our neighbor, we may or may not be eating Andromeda. We are actually eating Andromeda, and we will be merging with Andromeda. Yes, the party is here. Hello, Reese. Hello, Doro. Hi, John Foster. Yes, so at more smaller scales, as in, we are merging with Andromeda for sure. But at more large scales, as large scale in the universe, the universe is expanding. The discovery that the universe is expanding was one of the great intellectual revolutions of the 20th century. With hindsight, it is easy to wonder why no one had thought of it before. Newton and others should have realized that a static universe would soon start to contract under the influence of gravity. But suppose instead that the universe is expanding. If it was expanding fairly slowly, the force of gravity would cause it eventually to stop expanding and then to start contracting. The sun is still a very. Oh, let me share the live real quick. 1 second. Give me 1 second. Let me share the live real quick. The sun is still very young, and it will not be a red giant anytime soon. It has only done around 20 rounds around the galactic center, so sometimes we call it just a little bit older than a teenager. But but at some point the sun will go towards its next stages of evolution as a star, and the same sort of time. Oh my gosh. The same sort of time at which the sun would evolve to its next step, which is red giant, or not by the time it becomes a red giant, it doesn't even have to be its next step. During that timeline, along with that timeline, we will be merging with Andromeda. So I just noted that by the time we have merged with Andromeda, we will become an elliptical galaxy, and we won't even be the same shaped galaxy, and that's the same time during which the sun will be a giant. So yeah. Let me share the live. Who is lying? 6 billion years only for the Andromeda merger. 6 billion years. Well, we will start our merger sooner, but Andromeda and Milky Way will complete their merger. Will completely merge. That will take around 6 billion years. Who is meeting what? Ah, there you go. Okay, did someone share my live? Because I will now. I forgot to. Give me 1 second, please. Me never? Who's never? Who is never doing what? I'll share the live to my 0 followers. What about your secretary? You could share it to your secretary. What is happening? Okay, I see the comments now. I read that they discovered an anomaly between our two galaxies, so it's possible we're now interacting with Andromeda. Yes. Yes, we are. I think so. I think so. Why? Is that a surprise? Andromeda is a very close neighboring galaxy. So of course we are merging with Andromeda. It will just take us 6 billion years to finish merging, and the shape of our galaxy as the merged galaxy will be totally different. It will be an elliptical. No honey wine today. I might just have to go back to the Ethiopian place this week and get honey wine just for the sake of this live, since it seems to be so well liked. Should I go to the Ethiopian restaurant and get honey wine again? Go get you a British Indian GF. Already taken. There you go. People are already taken. Okay. It's Monday, maybe Friday. Friday I should go get honey wine. Okay. Sounds good. Okay, so we will keep going. I turned the page. So, the discovery that the universe is expanding was one of the great intellectual revolutions of the 20th century. With hindsight, it is easy to wonder why no one had thought of it before. Newton and others should have realized that a static universe would soon start to contract under the influence of gravity. But suppose instead that the universe is expanding. If it was expanding fairly slowly, the force of gravity would cause it eventually to stop expanding and then to start contracting. However, if it was expanding at more than a certain critical rate, gravity would never be strong enough to stop it, and the universe would continue to expand forever. This is a bit like what happens when one fires a rocket upward from the surface of the Earth. If it has a fairly low speed, gravity will eventually stop the rocket and it will start falling back. On the other hand, if the rocket has more than a certain critical speed, about 7 miles per second, it's a different number when you do kilometers per second, gravity will not be strong enough to pull it back. So it will keep going away from the Earth forever. This behavior of the universe could have been predicted from Newton's theory of gravity at any time in the 19th, the 18th, or even the late 17th century. Yet so strong was the belief in a static universe that it persisted into the early 20th century. Even Einstein, when he formulated the general theory of relativity in 1915, was so sure that the universe had to be static that he modified his theory to make this possible, introducing a so-called cosmological constant into his equations. This is the cosmological constant that I was talking about. So, Einstein introduced a new anti-gravity force, which, unlike other forces, so this is the anti-gravity, whatever you want to call it, basically the force kind of that that stabilizes the universe against gravitation. This is what he introduced, the cosmological constant. He introduced this into his equations, which, unlike other forces, did not come from any particular source, but was built into the very fabric of space-time. He claimed that space-time had an inbuilt tendency to expand, and this could be made to balance exactly the attraction of all the matter in the universe so that a static universe would result. Only one man, it seems, was willing to take general relativity at face value, and while Einstein and other physicists were looking for ways of avoiding general relativity's prediction of a non-static universe. So basically, Einstein introduced anti-gravity with the cosmological constant, and himself was sort of uncomfortable with that, you know. So once again, only one man, it seems, was willing to take general relativity at face value. And while Einstein and other physicists were looking for ways to avoid general relativity's prediction of a non-static universe, the Russian physicist and mathematician Alexander Friedmann instead set about explaining it. So this guy, Friedmann, was actually brave and embraced this anti-gravity type of stuff. And everybody, including Einstein, who himself worked on, obviously contributed and fathered general theory of relativity, was not so comfortable with the fact that the universe could be expanding and was in fact not static. So what did Friedmann do? Friedmann made two very simple assumptions about the universe: that the universe looks identical in whichever direction we look, and that this would also be true if we were observing the universe from anywhere else. From these two ideas alone, Friedmann showed that we should not expect the universe to be static. In fact, in 1922, several years before Edwin Hubble's discovery, Friedmann predicted exactly what Hubble found. So Friedmann did some cool math. We've kind of talked about that actually, with his equations and whatnot. So we will see what Friedmann did. The assumption that the universe looks the same in every direction is clearly not true in reality. For example, as we have seen, the other stars in our galaxy form a distinct band of light across the night sky, called the Milky Way. But if we look at distant galaxies, there seems to be more or less the same number of them. So the universe does seem to be roughly the same in every direction, provided one views it on a large scale compared to the distance between galaxies, and ignores the differences on small scales. For a long time, this was sufficient justification for Friedmann's assumption as a rough approximation to the real universe, but more recently, a lucky accident uncovered the fact that Friedmann's assumption is in fact a remarkably accurate description of our universe. Hello! Swinging from the cat tower singing Wrecking Ball? There's Baji! He's the one who's on the cat tower right now. Thank you. In 1965, two American physicists at the Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, so more people now, we're testing a very sensitive microwave detector. Microwaves are just like light waves. So microwave is, of course, another type of light with a different wavelength as visible light, for example. So microwaves are just like light waves, but with a wavelength of around a centimeter. So depending on the wavelength, we get a different type of light, and we call it microwave. In this case, you could have X-rays. If you had even smaller wavelength, you could have gamma rays with even smaller wavelength and such. Penzias and Wilson were worried when they found that their detector was picking up more noise than it ought to. The noise did not appear to be coming from any particular direction. First, they discovered bird droppings in their detector, so little poopies from birdies, and checked for other possible malfunctions, but soon ruled those out. They knew that any noise from within the atmosphere would be stronger when the detector was not pointing straight up than when it was, because light rays travel through much more atmosphere when received from near the horizon than when received from directly overhead. The extra noise was the same whichever direction the detector was pointed. So this is in whatever direction the detector was pointed, you're getting this extra noise. So it must come from outside the atmosphere. So, because all the different directions that you can point your detector will give us different types of atmosphere that the light would be traveling through. But if it's the same noise, no matter which direction, then it should be coming, whatever it is, should be coming from outside the atmosphere. It was also the same day and night. So same signal, same extra stuff. Oh, whoops. Oh, gosh. Oh, gosh. No, 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 no. Let's do this where I go back to the normal. I'm trying to clip something. Oh my gosh. I'll do the green screen in a bit. Give me 1 second. I clicked on it by mistake. I didn't mean to. I call them extra noise no matter what direction you pointed your detector towards. It was also the same noise whether it's day or night and throughout the year. So these people were checking for a long time, I suppose, even though the Earth was rotating on its axis and orbiting around the sun. This showed that the radiation must come from from beyond the solar system. So, again, same day and night and throughout the year, even though the Earth was rotating on its axis and orbiting around the sun. This showed that the radiation must come from beyond the solar system and even from beyond the galaxy. So, from beyond our own galaxy, as otherwise it would vary as the movement of Earth pointed the detector in different directions. Because we do see, for example, as you know, our galactic center is very bright. So if you point towards there, you will pick that up. But if you're getting this extra noise, no matter how you point your detector, no matter day or night, no matter what time of the year, and all that, we basically get something which must be coming from beyond the galaxy, as otherwise it would vary as the movement of Earth pointed the detector in different directions. As we go around our sun, for example, we kind of change. We're moving in the solar system. In fact, we know that the radiation must have traveled to us across most of the observable universe, and since it appears to be the same in different directions, the universe must also be the same in every direction, if only on a large scale. So this is true on a large scale. So this is not true when we're considering our nearby neighbors. For example, Andromeda is a neighboring galaxy. But on a large scale, the universe must be the same in every direction. We now know that whichever direction we look, this noise never varies by more than a tiny fraction. So Penzias and Wilson had unwittingly stumbled across a remarkably accurate confirmation of Friedmann's first assumption, because Friedmann assumed this. Friedmann actually assumed an isotropic universe when he was doing the math with Einstein's equations. And we kind of read about that from Einstein's Cosmos. So this actually kind of made sense now. We actually observed this at this point, confirming what Friedmann had assumed. So we now know that whichever direction we look, the noise never varies by more than a tiny fraction. So Penzias and Wilson had unwittingly stumbled across a remarkably accurate confirmation of Friedmann's first assumption, which is the isotropic universe. However, because the universe is not exactly the same in every direction, but only on average, on a large scale, the microwaves cannot be exactly the same in every direction either. There have to be slight variations between different directions. These were first detected in 1992 by the Cosmic Background Explorer satellite, COBE. I keep saying microwave because oh my gosh. Hello, Batman. Hello, everybody. Hello, Rose Dawson. Hello, Reese and Doro and Steven and all my other friends. Thank you for coming to the live. Thank you for being in the live. welcome to the live, and thank you, and please do like the live. Rose is here. Rose came in to defend herself. I mean, I'm ready. I'm ready for some Rose defense. So, once again, this is actually quite important. We've talked about the cosmic microwave background radiation, as you know, from during our cosmology lives, and so indeed we will get a little bit of a review for it. But let's just recap or read this part again. So, no matter whichever direction we look, this noise never varies by more than a tiny fraction. So there is a little bit of a variation, but it's not more than a tiny fraction. So Penzias and Wilson had unwittingly stumbled across a remarkably accurate confirmation of Friedmann's first assumption. First assumption of isotropic universe is basically kind of true, kind of pretty accurately true, as in if there's variations, it's not more than a tiny fraction. However, because the universe is not exactly the same in every direction, but only on average, on a large scale, the microwaves cannot be exactly the same in every direction either. There is a little bit of variation. There have to be slight variations between different directions. These were first detected in 1992 by the Cosmic Background Explorer Satellite, or COBE, at a level of about 1 part in 100,000. So these are literally 1 part in 100,000 level of variations. Small though these variations are, they're very important, as will be explained in chapter 8. So in this same book, we will talk about these tiny variations. I have to read this. Oh, I see, it's just Batman. Oh, goodness gracious. Hello, Batman. Hello, Reese. Hello, Doro. Hello, Steven. Hello, everybody. Thank you so much. Can we get 20 likes? John Foster is asking, random question. What made you want to become an astrophysicist? Well, I really like astrophysics. I just love the topic. Initially, I wanted to be a physicist. Like, I liked physics, but really, it was this type of stuff that I liked the most, like cosmology, universe, astrophysics, that type of thing. Hello, all. Steven says backwardly, ole. Hello, ole. So, COBE, another very important explorer satellite, picked up on these variations, and we will talk about them in chapter 8. I'm actually looking forward to that, because remember, these tiny variations in the cosmic microwave background radiation are potentially hiding a lot of little truths about the universe, let's just say. So we will definitely dive into that. We will definitely dive into that in the appropriate chapter from this book. And since this book is very simply written, I'm hoping that it will illuminate a lot and give us nice explanations. So was it in high school that you wanted to become an astrophysicist? No. It was in 7th grade. Stop normalizing the chat. Let him ask what he wants to ask, Reese. Are you a mod, or are you a goon nowadays, Reese? So it was 7th grade, whatever that is, middle school maybe. I went to school in India, so we don't have elementary, middle, and high school. We just have school. Oindri said goon. Gooning is something else. Okay. Like like what? What is it compared to what this is? Aww. Elon Musk lied about. Aw, you should write a book about yourself. Oh, thank you. Thank you. Thank you, Doro. Thank you, John Foster, Reese. Batman, I'm not reading everything from you, and that is going really well. 42. Molybdenum's atomic number is 42. I do like the answer 42. It's the atomic number of molybdenum, if I'm not mistaken. Hey Google, what is the atomic number of molybdenum?
Molybdenum has atomic number 42.
There you go. MSNBC. Okay. At roughly the same time as Penzias and Wilson were investigating noise in their detector, two American physicists at nearby Princeton University, Bob Dickey and Jim Peebles, were also taking an interest in microwaves. They were working on a suggestion made by George Gamow, once a student of Alexander Friedmann, that the early universe should have been very hot and dense, glowing white hot. Dickey and Peebles argued that we should still be able to see the glow of the early universe. Because light from very distant parts of it would only just be reaching us now. However, the expansion of the universe meant that this light should be so greatly redshifted that it would appear to us now as microwave radiation. Dickey and Peebles were preparing to look for this radiation when Penzias and Wilson heard about their work and realized that they had already found it. For this, Penzias and Wilson were awarded the Nobel Prize in 1978, which seems a bit hard on Dickey and Peebles, not to mention Gamow. Thank you so much for coming to this live. Can we please get 20 likes? Now, at first sight, all this evidence that the universe looks the same whichever direction we look in might seem to suggest that there is something special about our place in the universe. In particular, it might seem that if we observe all other galaxies to be moving away from us, then we must be at the center of the universe. There is, however, an alternate explanation. The universe might look the same in every direction as seen from any other galaxy too. This, as we have seen, was Friedmann's second assumption, that the universe is the same no matter where you're looking from, as in same in every direction no matter where you're looking from. We have no scientific evidence for or against this assumption. We believe it only on grounds of modesty. It would be most remarkable if the universe looked the same in every direction around us, but not around other points in the universe. That would make us kind of special, and we don't think that we're that special. In Friedmann's model, all the galaxies are moving directly away from each other. The situation is rather like a balloon with a number of spots painted on it being steadily blown up. As the balloon expands, the distance between any two spots increases, but there is no spot that can be said to be the center of the expansion. Moreover, the farther apart the spots are, the faster they will be moving apart. Similarly, in Friedmann's model, the speed at which any two galaxies are moving apart is proportional to the distance between them. So it predicted that the redshift of a galaxy should be directly proportional to its distance from us, exactly as Hubble found. Despite the success of his model and his prediction of Hubble's observations, Friedmann's work remained largely unknown in the West until similar models were discovered in 1935 by the American physicist Howard Robertson and the British mathematician Arthur Walker in response to Hubble's discovery of the uniform expansion of the universe. Isn't happy-go-lucky today? I'm happy, and I hope that I'm lucky. BJ, how are you? I am happy, trying to be lucky. BJ, how is South Korea? How is the universe in South Korea? I'm good, how are you? Tell us something about South Korea, BJ. Good to see you. Although Friedmann found only one, there are in fact 3 different kinds of models that obey Friedmann's 2 fundamental assumptions. In the first kind, which Friedmann found, the universe is expanding sufficiently slowly that the gravitational attraction between the different galaxies causes the expansion to slow down and eventually to stop. She made me laugh earlier. Aww. Do you have a Milky Way outfit? Oh my gosh, I need one. Thank you for suggesting it, John Foster. I do need a Milky Way outfit. Indeed. Thank you. Thank you so much, everybody. Can we get 20 likes? So, in the first kind, which Friedmann found, the universe is expanding sufficiently slowly that the gravitational attraction between the different galaxies causes the expansion to slow down and eventually to stop. The galaxies then start to move toward each other, and the universe contracts. It starts at 0, increases to a maximum, and then decreases to 0 again. In the second kind of solution, the universe is expanding so rapidly that the gravitational attraction can never stop it, though it does slow it down a bit. So, this figure, we will look at it shortly here, shows the separation between neighboring galaxies in this model. It starts at 0, and eventually the galaxies are moving apart at a steady speed. So basically, we have three scenarios here. We have figure 3.2, 3.3, and 3.4. We will see separation of 2 galaxies is in the y-axis and time is in the x-axis in these figures. And we will see basically the first example is going from a big bang to expansion to a big crunch. Then we just see big bang and just expansion, no crunch. And then we see a different kind of expansion. Thank you for being hooked to the live. Thank you so much. Thank you so much. Thank you. The moon's craters? We just didn't agree on how they were made. They're made due to impacts with planetesimals. But thank you so much for being in the live, coming to the live and becoming hooked. Most appreciated. So, it starts at 0 and eventually the galaxies are moving apart at a steady speed. Finally, there is a third kind of solution in which the universe is expanding only just fast enough to avoid a recollapse. So expansion doesn't have to be at the same rate. Depending on your model of cosmology, it could be going slower or going faster. Maybe it just goes fast enough to avoid a recollapse. Okay? In this case, the separation shown in this last type of figure that we'll look at also starts at 0 and increases forever. However, the speed at which the galaxies are moving apart gets smaller and smaller, although it never quite reaches 0. So that's what's going on here. Let's look at Sachi Mama real quick. Hello, Sachi. Hi. 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 She called me a monkey. Do you see Sachi, Mama? Right here. Hi. Oh gosh. She doesn't like being held. Give me 1 second. Oh, Sachi! Oh! Oh my goodness. There. I present to you my Baji Baba for a bit. Give me 1 second. I'm here. Sorry. I had to call a family member. I see some comments from Steven. Hello, Steven. And my alarm started going off. Okay. Hello, I'm back. I did these with my hair. I came back. I had to bathroom and then I got a phone call. Okay, we'll read a little bit more. Actually. Giving birth. Oh, things are not so good right now. I have an issue with somebody in my life. Oh well. So anyway, so we will look at, so by the way, I didn't show you the 3 pictures. Here is the Big Bang to Big Crunch, just Big Bang and then expansion, and then Big Bang and then expansion at a rate fast enough to avoid recollapsing. So, third kind of solution in which the universe is expanding only just fast enough to avoid recollapse. In this case, the separation shown in this last thing that I showed also starts at 0 and increases forever. However, the speed at which the galaxies are moving apart gets smaller and smaller. The speed at which the galaxies are moving apart gets smaller and smaller, although it never quite reaches 0, right? That speed. A remarkable feature of the first kind of Friedmann model is that in it, the universe is not infinite in space, but neither does space have any boundary. Gravity is so strong that space is bent round onto itself, making it rather like the surface of the Earth. If one keeps traveling in a certain direction on the surface of the Earth, one never comes up against an impassable barrier or falls over the edge, but eventually comes back to where one started. Combat sports! Hello! Hello. Combat sports for real says, oh, still here. Reese, hello, thank you. Steven, hello in reverse, thank you. Can we get 20 likes? So, gravity is so strong that space is bent around onto itself, making it rather like the surface of the Earth. If one keeps traveling in a certain direction on the surface of the Earth, one never comes up against an impassable barrier or falls over the edge, but eventually comes back to where one started. So like if I start just moving from here in Boston and keep on traveling the Earth, I will come back to this point at some point. In the first Friedmann model, space is just like this, but with 3 dimensions instead of 2 for the Earth's surface. The 4th dimension, time, is also finite in extent, but it is like a line with 2 ends or boundaries, a beginning and an end. We shall see later that when one combines general relativity with the uncertainty principle of quantum mechanics, it is possible for both space and time to be finite without any edges or boundaries. The idea that one could go right around the universe and end up where one started makes good science fiction, but it doesn't have much practical significance because it can be shown that the universe would recollapse to 0 size before one could get around. Thank you. you would need to travel faster than light in order to end up where you started before the universe came to an end, and that is not allowed. We know that the speed of light in vacuum is a constant of nature, and you can't go above that speed. Good night. Good night, Reese. Good night, everybody who needs to go. Thank you so much for being here. Thank you so much for coming to the live. See you tomorrow. Thank you so much. Thank you, thank you, thank you. Welcome to the live, and also see you next time. See you tomorrow. And if you have to go because you have to sleep, so be it. Thank you so much. Love to everybody. Thank you. Thank you for the hearts. The idea that one could go right around the universe and end up where one started makes good science fiction, but it doesn't have much practical significance because of the whole light speed thing. Okay? It's not allowed to go faster than the speed of light in vacuum. In the first kind of Friedmann model, which expands and recollapses, space is bent in on itself like the surface of the Earth. It is therefore finite in extent. In the second kind of model, which expands forever, space is bent the other way. Hi, Mohit. Hello. Thank you so much. Welcome to the live. Thank you. Thank you, thank you, thank you. Thank you so much for coming to the live, and also thank you for liking the live. Appreciate it. So in the first kind of Friedmann model, which expands and recollapses, space is bent in on itself, like the surface of the Earth. It is therefore finite in extent. In the second kind of model, which expands forever, space is bent the other way, like the surface of a saddle. So in this case, space is infinite. Finally, in the third kind of Friedmann model, with just the critical rate of expansion, space is flat and therefore is also infinite. Good morning, good afternoon, good evening to you, Mohit. But which Friedmann model describes our universe? So that's the question, because the nice thing in cosmology is that you can have various types of models which will give you sort of a different type of universe, but then you can ask, well, which one fits our reality the best, our observations the best? Oh, thank you. I leave you on my stereo on Bluetooth so I can hear you everywhere around the place. Thank you so much. Thank you, Peter. Welcome to the live. Thank you so much for being here. I appreciate your support so much. Thank you, Reese. Thank you, Mohit. Thank you, Peter. How is Australia? Is everything good in Australia now? I guess your fall is soon. Hopefully you had a nice summer, and hopefully you're getting ready for the winter. But which Friedmann model describes our universe? Will the universe eventually stop expanding and start contracting, or will it expand forever? To answer this question, we need to know the present rate of expansion of the universe and its present average density. If the density is less than a certain critical value, determined by the rate of expansion, the gravitational attraction will be too weak to halt the expansion. If the density is greater than the critical value, gravity will stop the expansion at some time in the future, and cause the universe to recollapse. So if the density is greater than the critical value, gravity will stop the expansion at some time in the future and cause the universe to recollapse. So it's all about this energy density situation that we have talked about a bunch during our strictly cosmology lives. In general, we have talked about it in astronomy, astrophysics, and cosmology lives, but especially in the lives where we talked about the cosmic inventory. I believe might have named the lives something like cosmic inventory or dark energy, dark matter, or ingredients of the universe, or energy density. If you look these things up in the live tab on my channel, we've definitely talked about this. So this energy density quantity that we're mentioning here is very important. So let's read that again. If the density is less than a certain critical value determined by the rate of expansion, the gravitational attraction will be too weak to halt the expansion. If the density is less than a certain critical value determined by the rate of expansion, the gravitational attraction will be too weak to halt the expansion. If the density is greater than the critical value, then gravity will stop the expansion at some point in the future and cause the universe to recollapse. We can determine the present rate of expansion by measuring the velocities at which other galaxies are moving away from us using the Doppler effect. So this is what we spoke about, which is that we saw that the spectra of those stars in the other galaxies were redshifted, so we know that they were moving away. So now this Doppler effect thing we just spoke about, this can be done very accurately. However, the distances to the galaxies are not very well known because we can only measure them indirectly. So all we know is that the universe is expanding by between 5% and 10% every 1,000 million years. However, our uncertainty about the present average density of the universe is even greater. If we add up the masses of all the stars that we can see in our galaxy and other galaxies, the total is less than 1/100th of the amount required to halt the expansion of the universe, even for the lowest estimate of the rate of expansion. Ooh. Our galaxy and other galaxies, however, must contain a large amount of dark matter that we cannot see directly, but which we know must be there because of the influence of its gravitational attraction on the orbits of stars in the galaxy. So we talked about the cosmic inventory, the 5 ingredients of the universe. These were photons, neutrinos, dark matter, baryons, that is ordinary matter, and dark energy. So we saw how ordinary matter was actually only 5% contributing to the energy density. And there was a bunch of this other type of matter, invisible matter, dark matter, matter that did not interact with light or photons, which we can't really see, or which does not contribute to the luminosities that we see, but it does interact with gravitation and did impact the orbital speeds of objects that were rotating around the galactic center, for example. So we cannot, let's read this part again. Our galaxy and other galaxies must contain a large amount of dark matter that we cannot see directly. So this is that particular ingredient we're talking about again. Again, the 5 ingredients are, did I say everything? Photons, neutrinos, baryons, or ordinary matter, dark matter, and dark energy. So those are the 5 cosmic ingredients, or the cosmic inventory, contributing to the energy density. Dark energy is a big contributor, turns out 70%, and it actually leads to us being able to say that we have an expanding universe, or this whole thing about the expansion of the universe is accounted for by this particular ingredient, which is dark energy. Hi, here is Sachi Mama. Hi, Sachi. Hi. 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 Look at this. Hello. Yay. Sachi Mama wanted to say hi. Thank you for all the comments today. Thank you for all the chat messages today. I really appreciate it. Thank you. Kind of everybody. And also thank you for chatting amidst yourselves. That also really helps. As in, I feel like everybody's making friends here and being engaged. So thank you so much. Oh gosh, Suji Mama almost fell. This is some granite and she slipped a little bit. Hi, Suji. Let me give her some love. Hello. Thank you for joining if you're joining. I went and put my hair into braids and I had to make a phone call. But I'm happy to see that everybody caught up with everybody during that time. And here we are again. I have a little eye booger in the meantime. Oh gosh. Hi, Sachi. Hi. Oh gosh. Hello. Hi, Sachi. Do you want to be in Mama's lap? She's actually, um, she is turning on the laptop lights and stuff. So, hello. So, let me read this part. Let's see. Our galaxy and other galaxies, however, must contain a large amount of dark matter that we cannot see directly, but which we know must be there because of the influence of its gravitational attraction on the orbits of stars in the galaxy. So that's the dark matter evidence that we are talking about. Moreover, most galaxies are found in clusters, and we can similarly infer the presence of yet more dark matter in between the galaxies in these clusters by its effect on the motion of the galaxies. When we add up all this dark matter, we still get only about 1/10 of the amount required to halt the expansion. So even when we add up all the dark matter, so this is where dark matter and dark energy are not the same thing. Dark matter has to do with all this extra matter, the invisible matter that ordinary matter or baryons don't account for. And then dark energy has to do with the expansion of the universe. So the model which says that this is the energy density, this is the contribution of each thing. Basically, if we had enough matter, the expansion of the universe would go a certain way. It's almost like we have all this stuff that we're seeing. Some of it is dark matter, which we don't fully understand, but we get it, that it's there. And then it's a matter of plugging in the last bit that's needed to actually fit the observation part of our universe and the fact that we know it's observed to be expanding. So if you don't have this last bit, then it's not going to account for the expansion of the universe. So that last bit is dark energy, and how much of it is needed, what model of it is needed, etc., is really determined by playing around with the models, playing around with the numbers, and then seeing what fits the cosmological model, which resembles the actual observations the closest. And we have observed expansion of the universe. It's not just a theory or a guess. We observe it to happen. So we can now plug in the type of ingredient, last type of ingredient or dark energy that we need for that expansion, for the expansion of the cosmological model, for the cosmological model that gives us the expansion that we would expect, that we actually see in observation. Because you can have a universe that's expanding less fast, more fast, in some other way, but the model of dark energy we need is the one that actually fits what we observe, right? So that's what's going on here. So when we add up all this dark matter, hi Acacio. Yes, so it looks like the universe is expanding, and it looks like we came from the Big Bang. And it's about, so there are a few different models of the universe. We could hypothesize that the universe started from a Big Bang, then it expanded, and then it might slow down and basically contract and become a big crunch. Or we might say that we came from the Big Bang, and then after that we're expanding rapidly, and it's just going to keep on expanding infinitely. And then we could also say that we came from the Big Bang. And by the way, evidence of Big Bang is now a lot. So pretty much we know we came from the Big Bang. We came from this singularity that created the universe. And then exactly how fast we expand could be we could have a different model of the expansion, basically. So then after that, we basically want to arrive at the answer that matches the observation. Because we know what kind of expansion we have in the universe, now we can tweak everything to make sure that we get that. And especially the 5 cosmic ingredients being photons, baryons, neutrinos, dark matter, and dark energy. Dark matter and dark energy are not well understood, but these two are both very important in the universe, it turns out. And basically after you have measured and figured out estimates for dark matter, the last ingredient, dark energy, is the one that's left. And that one, you could have many different models, but ultimately you want the model that fits our expansion observation the best. So yes, the universe is expanding. The expansion is in fact accelerating. We are reading about that right now from Stephen Hawking's book, A Brief History of Time. And yes, most likely it's infinite. We don't, I personally don't think that it's going to do a big crunch. And it's just a matter of figuring out what expansion model fits our observation the best. Mr. Ayub says, I'm back. Hi, Acacio. Hi, Peter. Hi, Mr. Ayub. Hello, everybody. Welcome to the live. Thank you so much for being here. I wanted to say hi to everyone, Mohit, Peter, Acacio, and Mr. Ayub. So let's keep reading, and I think it will sort of help to answer what you asked. And thank you so much for being here. Welcome to the live. All regular people, everybody, welcome. So, dark matter's evidence, there's different types of evidence for dark matter. One of the things is the orbital speed of objects that are revolving around the galactic center in our own galaxy. So there is evidence of extra matter that is invisible. We call it sometimes dark matter, invisible matter, whatever you want to call it. We just usually refer to it as dark matter. This evidence of it exists for even our own galaxy. We know that there is such things in our own galaxy, and then it also affects our neighboring galaxies actually. So, and clusters of galaxies. So there is this evidence of dark matter, but it's a separate topic from the expansion of the universe, although it's related or it can affect this last topic, which is the expansion of the universe. But the expansion of the universe is due to dark energy. See you next time, Mohit. Hi, Steven. So, moreover, most galaxies are found in clusters, and we can similarly infer the presence of yet more dark matter in between the galaxies in these clusters by its effect on the motion of the galaxies. When we add up all this dark matter, we still get only about 1/10 of the amount required to halt the expansion. However, we cannot exclude the possibility that there might be some other form of matter distributed almost uniformly throughout the universe that we have not yet detected, and that might still raise the average density of the universe up to the critical value needed to halt the expansion. The present evidence therefore suggests that the universe will probably expand forever. This is what Acacio was asking. But until there's more evidence of things that may come up, we basically are finding the evidence that the universe is probably going to expand forever. Because so far, what we see is suggesting that. So the present evidence, taking into account dark matter, ordinary matter, everything else, and the expansion, we think that it will probably expand forever. But all we can really be sure of is that even if the universe is going to recollapse, it won't do so for at least another 10,000 million years, since it has already been expanding for at least that long. So, do we know extremely concretely? Not really, but here's your answer I think that you wanted, which is the present evidence, which suggests expansion of universe. It gives us dark matter, ordinary matter, photons, neutrinos. Those are the 5 types of things. The present evidence therefore suggests that the universe will probably expand forever, but all we can really be sure of is that even if the universe is going to recollapse, it won't do so for at least another 10,000 million years, since it has already been expanding for at least that long. This should not unduly worry us. By that time, unless we have colonized beyond the solar system, mankind will long since have died out, extinguished along with our sun, because also, unfortunately, our sun is going to be evolving as a star during that timeline. Our sun is a very young star on the main sequence of its lifetime right now, but give it some more time, another billion years or so, order of billions of years, it will definitely evolve to a red giant, and that will create some issues for us in our present state of being on Earth. So all of the Friedmann solutions have the feature that at some time in the past, between 10 and 20,000 million years ago, the distance between neighboring galaxies must have been zero. At that time, which we call the Big Bang, the density of the universe and the curvature of space-time would have been infinite. Because mathematics cannot really handle infinite numbers, this means that the general theory of relativity on which Friedmann's solutions are based predicts that there is a point in the universe where the theory itself breaks down. Such a point is an example of what mathematicians call a singularity. So ultimately, the Big Bang is considered to be a singularity. In fact, all our theories of science are formulated on the assumption that space-time is smooth and nearly flat. So they break down at the Big Bang singularity where the curvature of space-time is infinite. This means that even if there were events before the Big Bang, one could not use them to determine what would happen afterward, because predictability would break down at the Big Bang. Correspondingly, if, as is the case, we know only what has happened since the Big Bang, we could not determine what happened beforehand. As far as we're concerned, events before the Big Bang can have no consequences, so they should not form part of a scientific model of the universe. We should therefore cut them out of the model and say that time had a beginning at the Big Bang. So this is also part of the discussion of this book, which is called A Brief History of Time by Stephen Hawking, which is that does the concept of time really make sense for before the Big Bang? Pretty much the concept of time is kind of starting at the Big Bang. That is sort of t equal to 0 for us in this universe. We don't know if there are other universes or what, but for this universe, the concept of time is really starting at the Big Bang, according to this author. Many people do not like the idea that time has a beginning, probably because it smacks of divine intervention. The Catholic Church, on the other hand, seized on the Big Bang model and in 1951 officially pronounced it to be in accordance with the Bible. I didn't know about this, but, if you say so. There were, therefore, a number of attempts to avoid the conclusion that there had been a Big Bang. The proposal that gained widest support was called the steady state theory. Yeah, that sounds familiar. It was suggested in 1948 by two refugees from Nazi-occupied Austria, Hermann Bondi and Thomas Gold, together with a Briton, Fred Hoyle, who had worked with them on the development of radar during the war. The idea was that as the galaxies moved away from each other, new galaxies were continually forming in the gaps in between from new matter that was being continually created. The universe would therefore look roughly the same at all times as well as at all points of space. The steady-state theory required a modification of general relativity to allow for the continual creation of matter, but the rate that was involved was so low, about 1 particle per cubic kilometer per year, that it was not in conflict with experiment. The theory was a good scientific theory in the sense described in Chapter 1. It was simple, and it made definite predictions that could be tested by observation. One of these predictions was that the number of galaxies or similar objects in any given volume of space should be the same wherever and whenever we look in the universe. In the late 1950s and early 1960s, a survey of sources of radio waves from outer space was carried out at Cambridge by a group of astronomers led by Martin Ryle, who had also worked with Bondi, Gold, and Hoyle on radar during the war. So Cambridge is very close to me. Happy to report. The Cambridge group showed that most of the radio sources must lie outside our galaxy. Indeed, many of them could be identified with other galaxies, and also that there were many more weak sources than strong ones. They interpreted the weak sources as being the more distant ones and the stronger ones as being nearer. Then there appeared to be less common sources per unit volume of space for the nearby sources than for the distant ones. This could mean that we are at the center of a great region in the universe in which the sources are fewer than elsewhere. Alternatively, it could mean that the sources were more numerous in the past and at the time that the radio waves left on their journey to us than they are now. Either explanation contradicted the predictions of the steady-state theory. Moreover, the discovery of the microwave radiation by Penzias and Wilson in 1965 also indicated that the universe must have been much denser in the past. So it's kind of like we were more dense, now we're expanding out and less dense. So it's kind of like this is further evidence of the Big Bang, actually, the fact that we came from a singularity, because there could have been, there were other theories actually for the beginning of the universe, for the beginning of time. But at this point, it looks like that there is actually solid evidence that we do come from the Big Bang. That is the beginning of time, basically. The steady state theory, therefore, had to be abandoned because Big Bang Theory won. And the show, Big Bang, is also named after that. So there we go. Another attempt to avoid the conclusion that there must have been a Big Bang and therefore a beginning of time was made by two Russian scientists, Evgeny Lifshitz and Isaac Kalatnikov in 1963. They suggested that the Big Bang might be a peculiarity of Friedmann's models alone, which after all were only approximations to the real universe. Only Friedmann's would contain a Big Bang singularity. So they're saying, is this just a part of Friedmann's math, which gives us the singularity, which is the Big Bang, blah, blah, blah. Is it real or is it just a mathematical concept that we get only from Friedmann's way of doing the calculation for the universe using general theory of relativity? In Friedmann's models, the galaxies are all moving directly away from each other. So it is not surprising that at some point in the past, they were all at the same place. So it's like, if everything is moving away, if everything's expanding, and that's how we are now, then at some point we were closer together. We were coming from a singularity. We were coming from this hot, dense, other, more initial state, or the Big Bang, basically, which the Big Bang is not really big or a bang, but it's the singularity that we're talking about, the beginning of the universe that we're talking about. The beginning must have been more hot, dense, contracted if we're less dense and expanded now. So in the real universe, however, the galaxies are not just moving directly away from each other. They also have small sideways velocities. So this is a cool way to put it. So again, in the real universe, however, the galaxies are not just moving directly away from each other. They also have small sideways velocities. So in reality, they need never have been all at exactly the same place, only very close together. Perhaps then the current expanding universe resulted not from a Big Bang singularity, but from an earlier contracting phase. As the universe had collapsed, the particles in it might not have all collided, but had flown past and then away from each other, producing the present expansion of the universe. How then could we tell whether the real universe should have started out with a Big Bang? What Lifshitz and Kalatnikov did was to study models of the universe that were roughly like Friedmann's models, but took account of the irregularities and random velocities of galaxies in the real universe. Because those irregularities and little sideways velocities do actually matter. They showed that such models could start with a Big Bang, even though the galaxies were no longer always moving directly away from each other, but claimed that this was still only possible in certain exceptional models in which the galaxies were all moving in just the right way. They argued that since there seemed to be infinitely more Friedmann-like models without Big Bang singularity than there were with one, we should conclude that there had not in reality been a Big Bang. They later realized, however, that there was a much more general class of Friedmann-like models that did have singularities and in which the galaxies did not have to be moving any special way. They therefore withdrew their claim in 1970. The work of Lifshitz and Kalatnikov was valuable because it showed that the universe could have had a singularity, a Big Bang, if the general theory of relativity was correct. We're almost done with this chapter, so we will keep going. However, it did not resolve the crucial question, does general relativity predict that our universe should have had a Big Bang, a beginning of time? So it's one thing to say that it could have had a Big Bang, a singularity, a beginning of time, but does the general theory of relativity say that it should have had a Big Bang, a beginning of time for our universe? Should versus could. Let's see. So, does general relativity predict that our universe should have had a Big Bang, a beginning of time? The answer to this came out of a completely different approach introduced by a British mathematician and physicist, Roger Penrose, in 1965. Using the way light cones behave in general relativity together with the fact that gravity is always attractive, he showed that a star collapsing under its own gravity is trapped in a region whose surface eventually shrinks to zero size. And since the surface of the region shrinks to zero, so too must its volume. All the matter in the star will be compressed into a region of zero volume, so the density of matter and the curvature of space-time become infinite. In other words, one has a singularity contained within a region of space-time known as a black hole. There is another singularity. At first sight, Penrose's result applied only to stars. It didn't have anything to say about the question of whether the entire universe had a Big Bang singularity in its past. However, at the time that Penrose produced his theorem, I was a research student desperately looking for a problem with which to complete my PhD thesis. This is Stephen Hawking, and he did work on, you'll see what he worked on. 2 years before, I had been diagnosed as suffering from ALS, commonly known as Lou Gehrig's disease or motor neuron disease, and given to understand that I had only 1 or 2 more years to live. In these circumstances, there had not seemed much point in working on my PhD. I did not expect to survive that long. So Stephen Hawking, very difficult diagnosis, and he thought that he wouldn't live that long to finish a PhD. Yet 2 years had gone by and I was not that much worse. In fact, things were going rather well for me, and I had gotten engaged to a very nice girl, Jane Wilde. But in order to get married, I needed a job, and in order to get a job, I needed a PhD. So, Stephen Hawking needed to get a PhD, and here we go. What did he do for his PhD? In 1965, I read about Penrose's theorem that any body undergoing gravitational collapse must eventually form a singularity. I soon realized that if one reversed the direction of time in Penrose's theorem so that the collapse became an expansion, the conditions of his theorem would still hold, provided the universe were roughly like a Friedmann model on large scales at the present time. Penrose's theorem had shown that any collapsing star must end in singularity. The time in a singularity must end in a singularity. Any collapsing star must end in a singularity. The time-reversed argument showed that any Friedmann-like expanding universe must have begun with a singularity. For technical reasons, Penrose's theorem required that the universe be infinite in space, so I could in fact use it to prove that there should be a singularity only if the universe was expanding fast enough to avoid collapsing again. So only if it is expanding fast enough to avoid collapsing again, since only those Friedmann models were infinite in space. During the next few years, I developed new mathematical techniques to remove this and other technical conditions from the theorems that proved that singularities must occur. The final result was a joint paper by Penrose and myself in 1970, which at last proved that there must have been a Big Bang singularity, provided only that general relativity is correct and the universe contains as much matter as we observe. There was a lot of opposition to our work, partly from the Russians because of their Marxist belief in scientific determinism, and partly from people who felt that the whole idea of singularities was repugnant and spoiled the beauty of Einstein's theory. However, one cannot really argue with the mathematical theorem. So in the end, our work became generally accepted, and nowadays nearly everyone assumes that the universe started with the Big Bang singularity. It is perhaps ironic that, having changed my mind, I am now trying to convince other physicists that there was in fact no singularity at the beginning of the universe. As we shall see later, it can disappear once quantum effects are taken into account. So he proved that there might have been a singularity. Now he's saying, well, maybe we don't need the singularity, and maybe there are quantum effects that can take care of the need for it. We have seen in this chapter how in less than half a century, man's view of the universe formed over millennia has been transformed. Hubble's discovery that the universe was expanding and the realization of the insignificance of our own planet in the vastness of the universe were just the starting point. As experimental and theoretical evidence mounted, it became more and more clear that the universe must have had a beginning in time until in 1970, this was finally proved by Penrose and myself on the basis of Einstein's general theory of relativity. That proof showed that general relativity is only an incomplete theory. It cannot tell us how the universe started off because it predicts that all physical theories, including itself, break down at the beginning of the universe. However, general relativity claims to be only a partial theory. So what the singularity theorems really show is that there must have been a time in the very early universe when the universe was so small that one could no longer ignore the small-scale effects of the other great partial theory of the 20th century, quantum mechanics. Yay! Finally, maybe these two will make up. At the start of the 1970s, then, we were forced to turn our search for an understanding of the universe from our theory of the extraordinarily vast to our theory of the extraordinarily tiny. That theory, quantum mechanics, will be described next, before we turn to the efforts to combine the two partial theories into a single quantum theory of gravity. So that's what we have here today, ladies and gents. We spoke about A Brief History of Time by Stephen Hawking. We covered the chapter 3, Expanding Universe is the name of this chapter, The Expanding Universe. It told us a lot of things about the universe, cosmology, the beginning of time, Big Bang, all that. And the next chapter is called The Uncertainty Principle, chapter 4, that we will talk about next tomorrow. So I do hope that you have enjoyed our book reading today by Stephen Hawking's, the book is authored by Stephen Hawking, and it's a very famous book that I think many people have read already, but hopefully you enjoyed this and our little discussion and chat and live, and we will be sure to catch you tomorrow. Thank you so very much. Thank you. Here you go, Suji. Oh, hi, Suji. Now we will hang out with the kitty cat. You look so young. Are you a professor? I'm not currently a professor. Thank you. Now we will enjoy a kitty cat. And we will start with the Uncertainty Principle chapter of Stephen Hawking's book, Brief History of Time, tomorrow. Hi, Suji. A physicist, yes, I did. Yes, I am a physicist. I have a PhD in physics in the subfield of particle astrophysics. Yes. And I've worked for some years after my PhD. So I am not quite that young, but good to feel young. Young still, not too young. And here is Sachi Mama. Thank you so much once again. maybe we can say hi to Baji as well before we retire to bed for the night, only to come back tomorrow for another lecture, another discussion, physics and cats field. We will reconvene tomorrow to chat about physics and kitty cats. To me, you look in early 20s. Thank you. Thank you so much. Thank you for being here, everybody. Really appreciate you. Hi, Sachi. Oh, good night. Thank you for joining, Acacio. Thank you for the questions. Thank you for engaging. Thank you for joining. Thank you so much. Thank you, Acacio. Thank you, Nausat. Thank you, Steven. Thank you, Mohit. Nausat, you should go back into the video and rewind and listen to the whole discussion. How are you, Nausat? Nausat is saying, hi, how are you? Like done. Thank you. Thank you. Thank you so much. How are you doing? Thank you for joining. You can rewind in the live so you can catch the whole thing. Thank you so much. Appreciate you. Thank you. Hi, Sachi Mama. Hi. Acacia said I'll follow you. I have more questions. A little more philosophical for next time. Sounds good. Oh, whoops, their food is about to fall. I'm gonna fix their bowls here. Fuji! They got their night meal. Come, Fuji. I'll give you your bowl separately. I'm trying to evenly distribute sometimes when I'm around, because Baji has been typically eating too much, and Kind of needs to be put on a little bit of a diet, actually. Thank you again for watching. Thank you for being here. Oh, Baji. You're still here. Hello. Mohit says, can we go to Mars and be back? I would like to tell you good night. Good night. Why is blue in animals so rare? Let's ask Suji. Why is blue in animals so rare? Hi, Suji. Good night to the chat. Indeed. I think Baji is using the bathroom right now. Oh, shoot. Oh my gosh. Baji? Oh my gosh. Oh my gosh. Okay, yeah, there was a big problem. Baji was going through the trash in the bathroom where I was putting it to store it in the meantime. Goodness gracious, it's quite a remarkable mess at this time. Right there, Baji tore into the trash. And it's my fault. Shouldn't have done that. Gosh. Baji, not good. That's not good, Baji. Not good. Indeed, very bad. Baji has been a bad boy. Baji tore into the trash, ate some kind of something, and did pretty bad things. Hopefully I caught it pretty quickly. just making sure all the trash is sorted so that Baji doesn't tear into it anymore. In fact, I might take it out right now. It's a little late, but, well, maybe tomorrow. It's a little late. And it was very rainy tonight. Well, today. All day, kind of rainy. So, not the best day for all these adventures. But Baji really tested out his limits today. thank you for your questions. I'll have to address these tomorrow. And I don't myself own a telescope, but thank you. Thank you for chatting. Thank you for chatting. Here is Baji Baba. Thank you. And here is Sachi Mama. All the little tigers right here.